Hello, everyone. Let me apologize right off the bat. Just getting over the end of a sinus infection. So a day or so ago, I would have sounded like I'd inhaled too much helium. It was a little squeaky. I was talking like this, but some of my timber is back. So I'm excited that I'm here today with two excellent colleagues, good friends actually. At this point, we've known each other for quite some time, and they've been huge supporters of this community. And so I can't tell you how excited I am to have them back. Before we begin, before I let them tell you all about UTT, which is an amazing advance in machine learning, I think everybody's going to be really excited when they hear more about it. Just a few housekeeping items. As usual, over on your GoToWebinar control panel, you have handouts. There are 3 handouts there today, including the slides that these guys will be using, and so please go ahead and download those. There's also a copy of the Universal Taxonomy, Technology Taxonomy itself, UTT. You can grab that and some other material that you might find valuable. But most importantly perhaps, is the opportunity for you to ask questions. We go ahead and ask you to go ahead and ask those questions as you come up with them. There'll be time at the end. We've scheduled this for about 40 minutes or so, just so there'll be plenty of time for conversation. You guys have always been so wonderful about adding questions and engaging with everybody, and to really asking really great technical questions and getting to the real core of what's going on. And that's some of the things that the sponsors love the most about this particular audience. And so, yeah, please go ahead and take advantage of that question section. Go ahead and put those in there. I'll be monitoring them. I'll stop the guys when it seems like it's a good time to ask some of those questions, and some we may keep until the end. There's also a very short survey at the end. Please just take a few moments. And the first question is really the most important one. Would you like to hear from Steve or Nigel about additional information about what you heard today? And if the answer is yes, then that's the easiest, quickest way for them to get back in touch with you and help you out with whatever it is that you need, or a demonstration, or an opportunity to use the system yourself with your own work in your own area. All right, so with all that out of the way, hello and welcome to episode 10 of the ML4Patents.com webinar series, this time featuring Cipher. My name is Tony Trippi. I'm the founder of ML4Patents, managing director of Patent Informatics, and IP manager for Owens Corning. I'm joined today by Nigel Swisher and Steve Harris from Cipher, and they will be talking, as I mentioned, about the Universal Technology Taxonomy. And with that, I will turn it over to Nigel.
Look, thanks, Tony. And first, a huge congratulations on the success of the ML4Patents series. For those people who have not listened to other episodes, I know all the episodes are available for viewing on the website, and I really recommend them. They're insightful. They're also very transparent. From all the people who come on here are very willing to expose the latest of their thinking. And this is a rapidly developing area. So those people who think that ML is done, it isn't. And as a resource, without wanting to go and celebrate Tony's work just too much, there's a podcast called Cipher Vision where we interviewed Tony about 2 weeks ago, and we put it on our platform. And I know, Tony, you've been boosting it. For those people who want to hear Tony's views about the evolution of ML, I thought that conversation was very insightful, just talking about how ML can help and why people should be paying very close attention. So thank you, Tony.
Oh, you're most certainly welcome. It was a great pleasure to spend 20 minutes talking to you guys. And probably for this audience, the biggest thing you're going to want to take away from that conversation is the idea of how critically important these listeners are to the continued development, that people with this particular skill set, patent information professionals, it's absolutely essential that you get involved as soon as possible and as much as possible, because this is just going to be something that all of your organizations are going to want to get involved with, and you're in a perfect position to be able to spearhead those efforts. And so we spent a fair amount of time talking about that and how critical it is that instead of looking at this as a challenge to this existing industry or this profession, it should instead be looked at as a launching pad. And again, so it's a great podcast. Please, I can put the we've got the URL for that in a variety of different places, but contact me if you'd like a copy of that yourselves.
Cool. And with a bit of luck, can everyone see the slide deck? Steve, can you see that?
Not yet, no.
Oh, that was not an ethically good start then.
There it is.
Cool. The structure of this presentation, as I say, we'll take the questions as they arise, but otherwise we've broken this introduction to the Universal Technology Taxonomy into 3 parts. First of all, as we always do, to start with why, then to look at the how did we go about the design and build phase, and then finally, of course, what do you end up with? So first of all, just a quick definition section. The Universal Technology Taxonomy is, as the name suggests, and as Cipher spends so much of its time working on, a taxonomy. It has 9 superclasses, and you can see those in the key on the top right-hand side. Mechanical, sensors and optics, life sciences, I won't read them all. There are 9 of them, and then the color coding shows that within each of those superclasses, as we call them, there are 114 in total subclasses. So you can see mechanical is broken down into airbags, bearings, clutches, and brakes. Really important that that taxonomy is understood, because the rest of this talk is about why this is so important. And for those people who are interested in scope notes, as you know, classification always puts patents into a bucket defined by reference to the human scope. Those scope notes are, as Tony said at the beginning, available for download. Now, why is classification so important? It is Cipher's why. We've spent the last 8 years trying to develop technologies, including ML, technologies to enable patents to be classified to technologies. But that isn't an end result. No one wakes up in the morning saying, I hope I have some patents sorted into piles. That isn't a data solution. That's just swapping one data problem for another. You've got to understand why that's important. So these are our whys. These are the Cipher 10 solutions that we think are supported by classification, benchmarking, enabling people to compare their portfolios with other portfolios, budget, being able to explain either to themselves, but typically to others, including the CFO, why portfolios cost what they cost and why budgets need to be increased, or to explain why they're spent in the way they are. Portfolio optimization, probably our bestseller, as we call it, explaining why a portfolio is the way it is, the size it is, and to answering the fundamental question, how many patents are enough, to avoid issues associated with understocking and overstocking. Competitive intelligence, the name suggests, and technology trends, watching global technology trends. The bottom line is a selection of other ones, which I'm not going to take the time today to go through, but I just wanted to drive home the message that the reason that people should be leaning into this webinar is to understand classification, of course it is, but to really ask themselves what problems would it solve. So after 8 years and tens of millions of dollars, what problem has Cipher solved? Well, it's to take the corpus of patent data, they say 40 million plus active patent families, and to allow them to be mapped into technology taxonomies. So what patents relate to location devices, what patents relate to lithium-ion batteries. We've always tried to go and solve that problem. And the important point is to try and automate it. There have been lots of technologies before Cipher, typically Boolean, that uses keywords and codes in order to try and do that. And the frustration that we were trying to overcome was it was never automated. You always ended up with another manual step. So Cipher's why is to automate the mapping of patents to technologies to enable evidence-based decisions in the areas I just described. We've done lots of surveys to validate the need. We did a survey on benchmarking and we almost got 100%, but 98% of organizations say they benchmark. No one's portfolio sits in isolation. We did another one about what level people did benchmarking, and 75% of organizations benchmark at a technology level. There are no prizes for saying, I have 1,000 patents. That just means you spend a lot of money. That isn't what your portfolio is or why it's performing its strategic functions. And then on the right-hand side, as a warm-up to why we developed the UTT, what are your challenges? Your challenge is that it's too expensive and time-consuming. Your challenge is there's no objective or reliable data. Your challenges are there's no accepted industry standard. Well, that's the game. Tony was kind enough on the introduction to say this was a game changer. So how does the Universal Technology Taxonomy, Steve, change the game?
So we, taking a step back and thinking about how we designed the taxonomy itself, we wanted, the universal in the name, we wanted the taxonomy to reflect the technologies people were actually filing in rather than being a design taxonomy. So typically when we work with clients, we will take their internal taxonomy or a derivation of it, and we'll build that out in software, because what we're trying to do is map the world of patents into terminology that matters to that company and that makes sense around their structure and their strategy. But in this case, you needed it to be something which everyone could use and make it sort of as neutral and representative as possible. So that kind of means that no one company's technology is represented really well, but also it means that everyone else that they deal with in their sector or suppliers or whatever, they can get an accurate view of what they've got. So the way we approached that was we took every family that are granted in the US in the last 10 years, and we clustered using an ML algorithm. We clustered the patents in there and then kept breaking it down until we had sort of these micro technologies of no more than 0.5% of the families that are granted in that time period. And then we looked through them to try and figure out what the technology was that had been identified by the unsupervised ML and the clustering algorithm. And then we grouped those up into sort of logically similar things that were roughly 1%, as close as we could get to that, in order to try and be sort of as hands-off and free of human design as possible. Obviously, there's a little bit of subjectivity in there, but we're trying to minimize that. And there's a few exceptions in there. There's a few technologies, like machine learning is a good example, where there wasn't actually 1% of coverage there, but it was growing so quickly, it was quite clear that within a couple of years, it would easily be up to 1%. And then we grouped each of those. So we ended up identifying roughly 100, it was 125 thereabouts. We slowed it down a little bit, but we identified 125 classes. We grouped them up into logical units. That's not in any way reflected in the way the ML works. I'll talk a bit about that in a minute. It's just to help humans navigate it, because a list of 120 classes is very, very difficult to navigate. So we wanted some structure in there to help people understand and help them find things. And we've got a visualization of, so this is the, we ended up with, I say, we killed off a few classes, which turned out to be too crossing over with other technologies, or where it made more sense to restructure it slightly. We ended up with 114, and you can see the super classes they're grouped into there. And you can also see that they're not completely even. There's two reasons for that. One, this chart is done from families that have a grant currently anywhere in the world, but excluding families that only have a grant in China, because it turns out the technological makeup in China is very, very different, specifically for China-only families. So this is different from the US cut that we originally designed the taxonomy of. And also there's some sort of impedance mismatch between when we were looking in the clustered classes that were discovered by the unsupervised ML and coming up with a human and scope note that describes that. there's often a little bit of disconnect between what the machine had covered and how we defined it when we were training the classifier. So between those things, there's a little bit of shift, but you can see that it's pretty narrow. The range with this cut, I think the largest one's around 2% and the smallest one's about 0.5%. So it's pretty it's pretty close to even. And then that's important, obviously, when we're dealing with these very, very broad technologies. We want to try and make sure as far as possible that we get a good spread of technologies when we're looking at a single company. And if you generate a landscape of one of these, you don't end up with some that just take up 20% of the world's patents and some which have almost nothing. So I'm going to talk a little bit now about where the UTT classifier itself sits in the technology and Cipher platform. So before UTT, we had two techniques for breaking down portfolios. The first thing we had was natural clustering, which is actually a very, very similar algorithm to the one that we used to design the taxonomy. But you give it a set of portfolios and you say to the machine, identify some key topics and assign everything in this portfolio to one of those key topics. So in this example, I've given it a portfolio of some company, it's identified 4 key topics, and it's assigned all the families in that portfolio to one of those topics. And it comes up with a sort of short paragraph of effectively keywords that are common in that technology in order to help you understand what it is. But the technology has been discovered by the machine, and it doesn't always match perfectly to how you think about the company, and it can be quite difficult to figure out exactly what things are included and excluded because it's only showing you examples. It's very difficult, but this problem of taking the results of an unsupervised clustering and then naming the classes is incredibly difficult, very famously difficult problem. And by contrast, the other technology that we had prior to the UTT was binary classifiers. This is typically how we work with our clients. So each of the ovals in that thing represents a class which has been scoped by a human, and then we've trained a classifier to match patterns to that scope just by giving it examples and counterexamples. Then you can run that over any set of patterns, and it will give you, hey, here are all the families that fall inside that scope. And that's quite nice. It's very flexible, particularly it allows for overlap. So you can see the orange and the cyan ovals that overlap. That's where there's patterns that fall into the scope of both of those classes. And that can be really useful, but there are cases where you don't want that. So we have options when you're running it where you can say, assign it to the most relevant one rather than assign it to both, depending on exactly what your use case is. But clearly, you're never going to pick up all of the white space in any portfolio unless you design millions and millions of classes. There'll always be something that falls outside. So you end up with these areas that can't be classified because they aren't covered by the taxonomy. And the UTTs kind of combines both of those things. So this is kind of a quick summary of where it sits in relation to clustering and binary classification. So it is supervised. The scopes were designed by a human. There's training sets behind that which allow it to learn what the definition of the technology is. It's also universal, meaning any family that you show it will fall into a class, which is clearly not true of binaries. I talked about the scoping before. It doesn't have clearly defined boundaries. I'll talk a bit about that in a second, but the binary classifier, you specify positives and negatives in the training set. So you say, here's examples of things that I want inside the technology, and here's the examples of things I want excluded. And the trainer of the classifier gets to say very precisely where they want that cutoff to be. In a multicast, that isn't the case, because everything gets assigned to something. It will inevitably end up being assigned to the thing which is closest to one of the 114 classes. So you don't have that boundary effect. If you did have a boundary effect, you would end up with things that don't get classified. Again, you don't get overlapping because the classifier is only able to say this family falls into class 27. It doesn't have any way of saying, I don't know what that is. You can use it to generate landscapes because you can just run the classifier over all the patents in the world and pull out all the ones relating to a particular class, which you can't do for clustering because the clusters don't have any identity outside of the set of patents that you feed into it. So there's no way to say, okay, great, you've identified this cluster relating to brake discs, now show me all the brake discs in the world, because it hasn't seen them. And it's not bespoke, of course, because it's meant to be universal. This is something we want everyone to be able to use. So it's not customized for a particular scenario or a particular client. It's just something which is what it is. And our intention is that we will do annual updates to the taxonomy based on filing trends or where we've observed that there's a new technology that's emerging that's now big enough to warrant its own class, or just based on our experience of using it. And then in terms of the speed, there's kind of like an order of magnitude improvement. Clustering is quite slow because it involves a lot of inspection of the data. Binary classification is relatively quick because we highly optimize the platform to make it quick. And the multi-class is even quicker, although there's an asterisk there because in actual fact, the processing that we use to do the classification is quite time consuming. But because it's only one taxonomy and every family in the world falls into a single class, we can cache the results. So we just pre-calculate it every week so that the results are already available. So from the end user's perspective, it's very fast, but in reality, it's actually quite computed.
Configured. So let me ask you a quick question before you jump off that slide. And because I think this is a really critical distinction between the binary or the bespoke, the customized taxonomies and the multi-class. Can either of you spend just a minute on, because I am assuming that theoretically you could have made this so that that a single document could appear in more than one class. So I'm guessing that there was a conscious decision, and there's pros and cons. I mean, people will go back and forth about if a patent, especially a family where there's divisionals and other items like that, a representative of different inventions, why it is that you folks made the decision to say, well, okay, this is the best representative example for the family, and therefore this is the one place that's going to go. Now, like I said, from an analysis perspective, it makes things so much easier, because when people look at things, I can't tell you how many times people get confused. They'll look at a line chart and they'll count up the sum of that and say, well, wait a second, there's only 500 families in this collection, but if I counted up those bars, that equals 2,000. Why is it that there's all this extra stuff? And then you have to explain, well, yeah, because some documents fall in all of the buckets, and this simplifies that to a degree. But again, it's a conscious decision. So maybe could you spend just a moment on the decision to go ahead and say, yeah, one family, one class?
Yeah, so that's the difference between a multi-class and a multi-label classifier. So there's a thing called a multi-label classifier, which we don't have, which allows it behaves a bit like a multi-class, but it allows, rather than picking a single class, it allows it to say, hey, it's actually representative of these two. But it's basically the reason you said. We were aiming this at, so if you think about it from the perspective of a Cipher user, they've got their own internal taxonomy, which covers all the technologies that they really care about. And that's the thing that they want in detail. And they can apply that exclusively. So it's tell me which class it best fits into, or with overlapping. So give me every class that this family relates to. And that's brilliant for sort of, some of these really sophisticated use cases like portfolio optimization, where you really need that level of control. But there's other cases where it's like, maybe I'm interested in Samsung's portfolio, so I can see that 5% of their portfolio falls into classes that I care deeply about. That means there's 95% of their portfolio, which is probably not of direct relevance to me, but I just want to get some insight into what's in there. So for the cases where you really want to use the UTT like that, for analyzing like companies which are largely not in my industry, or maybe it's a company you're thinking of acquiring and it's not in your tech space. You just want something that's really easy to understand, and presentations to the board. There's all kinds of these things where you just want like a very simple way of quickly breaking down a portfolio that's reliable, it's easy to understand, it's easy to present, it's easy to communicate. That's kind of really the sweet spot, because we're targeting use cases which are outside the core business of the client. So by definition, they don't want huge amounts of detail there. They just want something they can use to break down portfolios.
And Samsung's such a great example of that, because they're into just about everything.
Right.
And if you start to get into the details of exactly how far they are into some of these things, it really diminishes the general idea that from a broad perspective, they are mostly interested in this one. And these are the ones that are a sort of a secondary focus. And then, yeah, sure, they're doing stuff over here, but it's a small percentage of their overall portfolio, especially if it can be reapplied in one of the areas we've already covered. So
Right.
I really think that that's a great answer, and that's what you'd hope to do with something like that, is to be able to say, look, we already counted that one. You know, that's a semiconductor one. And so, yes, okay, we understand Samsung does semiconductors. And if we're going to talk about Samsung doing something else, it would be nice to know that it's not related to semiconductors. So, cool. Thank you.
Yeah, so this is a visualization of the difference between, I didn't include multi-label on this just to avoid making it more confusing, but this is the visualization of the difference between a binary and a multi-class classifier. They're actually, the technology is quite similar. It's just the way that they're trained and the way that they're evaluated is a little bit different. So in the binary classifier case, it knows about two classes. It's got the positive class and the negative class. So in this case, it's LiDAR and not LiDAR. And you give it examples of both of those things, and you show it a family, and it says, okay, this one we're giving it a score of 0.911, roughly equivalent to a probability. So there's 91% chance that it relates to LiDAR, and there's 8.9% chance that it doesn't. And that's fine. And we build taxonomies by stacking up dozens of binary classifiers, which allows you to play these tricks with it belongs to multiple or it belongs to one, and we'll assign it to the most relevant. The multi-class works in a slightly different way. So rather than having LiDAR and not LiDAR, you have LiDAR, radar, ultrasound, all the competing technologies, and it assigns a score to each of those. It tends to be highly skewed towards ones and zeros in the technology that we're using. So in this example, it's like 0.997 sure that it's LiDAR, and then there's like vanishingly small probabilities that it falls into some other class. That's actually overplaying it. The differences are, it's very much closer to one and very much closer to zero than that. The numbers would be quite long. But it has no way to say, I don't know what this is, because the only things it knows about in the universe of the 114 technologies it's been trained on, so everything you give it will fall into one of those. If you throw it some random patent like I don't know, window that can also be used as a fridge or something, it's just going to put it in a random class. We've all seen those crazy patents that just make no sense. So it has no way to say, I don't know what this is. It's forced to say it's closest to one of these 114 things. Yeah, when we were training, well, we're still training it, but while we were training it, we've been building up a test set, which is roughly 70,000 examples of families which we think fall squarely into one of the 114 classes. And as we've been training it, we're constantly evaluating the accuracy against those, that test set. And this is the F1 score of each of the individual classes rounded to the nearest 0.01. So you can see it scores very well. That's partly because the areas are quite broad. You know, it's relatively easy to tell them between a LiDAR and a radar sensor, for example, except when someone writes maybe LiDAR or radar, which they tend to do quite a lot. But on the whole, it's very accurate at that kind of level. And you can see there's some classes where we've still got some work to do, but the majority of them are more than acceptably accurate. And it's a little bit, the precision recall and F1 scoring for multi-class is a little bit different from binary, and not so much in the math. The maths is essentially the same, but scores tend to typically be a little bit lower because you've got, rather than one class where you might make an error, like you might say this is not LiDAR when actually it is, you've got 113 mistakes you might make for every particular family. So so these scores are actually pretty impressive, and it's partly because of the classification technology, partly because we've now got a really big, really sophisticated training set, and partly because the technology is pretty broad. So it's easy to build up a large training set with lots and lots of examples, which isn't always the case for our binary classifiers. You know, some of the training sets for our binary classifiers might only have 100, 150 families in them, because that's all the examples there are out there. Whereas these multi-class training sets are massive. It's 150,000 families or something in total. And this is breaking out the precision and recall independently. So you can see there's some which have got a fairly high degree of skew, and obviously the ones in the bottom left are the ones that we're working on at the moment, improving the accuracy. But overall, this is particularly for the kind of tasks that people use this sort of very broad taxonomy for, that's more than sufficient levels of accuracy.
So if I manage to go and master the technology, can you see Cipher, Steve?
Yes, we can see that. Before you launch into that, we do have one question that's been there for a few moments that I'd like to go ahead and ask you guys to address. And the second question just came in that I haven't read yet. So we'll see about talking about that one. But the first question is, and we get quite a bit of this, you know, there tends to be real concern in the pharmaceutical / life sciences arena with the usefulness and effectiveness of a lot of these methods. This is a pretty common question that comes up. So how do you handle? And the specific question is, well, how do you classify drugs, say the material itself, so the composition, versus the life science component, so the use of it for a disease therapy. So and that's sort of an example. How do you think the system would work? I noticed when you were on a previous slide, you know, you had materials including chemistry, and then you had life sciences, and so you had an entire life sciences section as well. So under ordinary circumstances, understanding that you know, there's no absolutes, but how would the system distinguish between something that's primarily a composition of matter, a patent that's associated with the substances, versus the method of treatment?
Yeah, so that is I mean, the first thing to say is that the coarseness of this taxonomy, it's only got 114 classes to cover the whole of technology, so they're really very big. So the life sciences categories are extremely broad. Some of them are a bit surprising just because of the weight of the weight of the patents is not where you might imagine. But it really comes down to whether the algorithm, so the scoping of the classes, I can't remember exactly what it will be, but chemicals probably has a life sciences exclusion. So it will be chemical compositions where there isn't an obvious application in life sciences, and the life sciences stuff will be covering things which have a particular function in life sciences. Now, there will obviously be cases where there's a chemical compound that's being patented, and an expert in the domain would look at that and say, well, that's clearly for a life sciences purpose, and the algorithm won't necessarily pick that up. unless it's seen enough examples with similar terminology that it can figure it out. But I wouldn't expect that to be the case. So those things will tend to fall between those two classes. But wherever there's a clear life sciences application for the compound, it will fall into one of the life sciences classes. But it's not, the taxonomy is way too broad to be able to split down particular compounds used in life sciences by their function. Like it could tell the difference between a heart disease drug and a liver disease drug just because there's not enough granularity in the taxonomy. The technology is perfectly capable of doing that. It's just not at this very coarse, everything in the world falls into one of 114 categories.
And it's sort of back, Tony, to the why at the beginning of the webinar. There are some use cases where the universal technology taxonomy is really useful because it does everything, and some where binary classification is much better because you want it to be narrower, you want it to be specific, you want it to make those fine distinctions. And of course, there are some, back to a previous webinar we did with you, where there are some things that ML can't do, which is sometimes to recognize the difference between two patents, where it's really important that that difference be understood. I think you had an example of two different types of apple, yeah, there are some small numbers, some small micro definitions that ML can't recognize the difference between.
Yeah, that's what I mean. Chemistry is a unique, distinct issue that also has other solutions associated with it. And so it's not the sort of thing that should be a high priority. Exactly. And yeah, I mean, that's just the thing. I mean, when you start getting into Red Delicious versus Granny Smith, you know, they're the same apple, almost, you know, to 98%. It becomes a challenge that you have to wonder, well, why are we even talking about that? It's much more important to identify apple, especially at this level. This is certainly an apple versus fish idea. If we were to use that continuum again, no, it's not apples and astronauts. Okay, that would not be useful. That's not helpful. And it's probably not apple oranges, although within the categories, you know, it's funny too, because I didn't want to point this out. It's almost like you've developed the periodic table of patents. You know, when I saw that original chart where you've got the columns and you know, it's like, oh, that's a periodic table. So that's the chemistry geek coming out. But I was like, the periodic table of patents. So I give you permission to go ahead and start using that in your marketing. But anyhow,
that was the visual inspiration, actually, the periodic table. But yeah.
But I mean, you know, we talk about, is it apples and oranges, and I don't really want to go and stay with the fruit analogy for too much longer. But you can see inside energy, batteries, fuel cells, the difference between hydroelectric and photovoltaics. Well, it's a little bit closer than apples and fish, I think.
Yeah, definitely.
Well, the apples and fish would both fall into food and drink, but so it's not.
Yeah, well, energy and electrical. Energy and electrical might be, in fact, you know, that sort of, you know, they're related, but they're not the same thing.
Right.
Meanwhile, all those things within energy, you know, definitely apples and oranges. So yeah, to kill an already battered analogy, you know, we'll just keep hammering away until we get it right.
Right, and it's important that when people look at the universal technology taxonomy with that kind of question, they don't say, and the universal technology taxonomy is therefore no use. They should say it's not useful for that problem. I always forget the exact wording of the trippy law of analytics, but it says, make sure you understand the question you're trying to answer before you find the tool.
Yeah, exactly. There are so many needs that this will address, and trying to shoehorn it into a need that it wasn't designed for doesn't do anybody any favors, because you're using the wrong tool. You're using a hammer instead of a screwdriver. Right. And nobody's going to like the results, especially the person who made the hammer. They don't like the idea that you're using the hammer to screw in nails. It doesn't work well. It doesn't reflect well on the hammer. So yeah, no, I couldn't agree more with that assessment. This is designed to do very important work and at a specific level and for a specific need. And it does it very, very well. And if you've got other issues, other needs, other questions, well, then let's talk about the correct solution for doing those.
Yeah, I mean,
Totally.
this is the third way we've come up with of breaking down portfolios of patents, and there's a reason for that, right? It's not the be all and end all. It's another tool in the toolbox that you need under certain circumstances.
Okay, so I volunteered to offer a short demonstration about the what. What do you end up with? So this is live Cipher, so anything could happen. But there's a tile in there which is called UTT Landscape Report, which all our subscribers can subscribe for. And I already highlighted this before. That's exactly the same structure as is on the newly named periodic table of patents. And if you wanted to go and know about the landscape, for example, in telecommunications, and you wanted to focus on location satellite, you would do that. You'd be reminded of the scope, and you'd be asked whether you wanted to use a cached report or run a new report. Running a new report takes about how long, Steve?
A couple of minutes.
But using a cached report takes a matter of seconds, and certainly bearing in mind I ran it before the call. So this is, I'm sorry, Steve, you gave away the fact that it was cached, because this is actually on one level just gone and classified 44 million patents in 1 second. Now that's what it feels like to the user, and that's what we want it to feel like to the user. They don't go and say, oh, you've cheated, you've cached it. The patience of users is, as our ML technologies get better and better, is rightly diminishing, and they don't want to wait. So these are all the 14,000 patent families, active patent families relating to location and satellite. As Steve said, there's a kind of bias towards China. So if you wanted in Cipher to exclude China, that would change the top owners just by filtering out those China-only families. And there you end up with the view of the top 15 owners. If you wanted to make it the top 20 owners, obviously it can all be manipulated, because Cipher now already knows all the owners of those patents, the patents relating to that technology inside the UTT. So instantaneous global landscapes. So that's use case number one when you're looking at technologies and you want to compare one technology to another. The other common way of using Cipher with UTT is to do it with an organization search. Same kind of question, rather than saying, saying, tell me everything about one technology, I want to know everything about a set of companies. So bearing in mind you chose Samsung, I'm about to go and set a Herculean challenge, because Samsung on its own, as you can see, has 150,000 families at the group level. If I want to add in, let's choose another monster, LG. And you can see when we're doing this LG, Cipher's, and this is, we've already talked about these corporate grouping challenges, but Cipher has already dealt with the corporate grouping. That isn't ML, that is blood, sweat, and tears. But it's really important that the analytic systems of today and tomorrow bring in the right solutions. And if it's manual, do it manually. If it's algorithmic, doing algorithmically. And if it's ML, that's great. But you can keep on adding companies. Now, the report I created before, I'm going to stop at those two companies. You can see that the Cipher users are asked, do they want to use clustering? That was the unsupervised ML Steve spoke about at the start. And there's the UTT. So now we select the UTT and run the report. As it happens, that takes a little bit longer. And so before this call, I added in Mitsubishi, Qualcomm, Samsung, Huawei, Thales, and it took about under 15 minutes. And it generated this report. So that's taking those companies and running all 114 classes against those portfolios. So that has classified 405,000 patent families using the speed times that Steve was talking about before. Now there's the point that you were making before, Tony. You've got a very good idea about where the focus area, where the concentration areas are. And if you want to go and compare one company to another, you can filter by technology, you can filter by territory, you can filter by time and make that comparison. So for example, if you wanted to focus on LG, you would simply eliminate all the other companies. That would give you basically an LG view only. you would take another view in Cipher, which is active families by technology, and now you'd be saying, what's LG doing? And now you can see this is only LG and their humble 128,000 patent family estate, broken down by, and you can see they have very broad tech company, has technologies in all 114 areas. And in this view, we're simply showing you the top 15. So you can see that the largest technology area that LG own is displays, closely followed by, well, not so closely followed by, with batteries at 9.8%, wireless networks at 7.8%. And that enables you to do these high-level analyses. So I know that's the quickest demonstration of all, but we always try and keep the sort of a demo part light. If anyone wants to go and see a demonstration of this in slow motion, they should just reach out to Steve or to me or to you, Tony, and we'd be more than happy to go and do something more detailed. But I just wanted to go and give that feeling of technology landscapes, and also that feelings of organization analysis, which are the two primary uses of the UTT. And with a bit of luck, that should have stopped the screen sharing.
Yeah, and that was brilliant. And when we have 5 questions already queued up, and we are a little bit past 45 minutes. 90% of our audience is still with us, so thank you, everybody. Yes, take the survey, say yes, I'd like to learn more, and these guys will reach out and contact you. So I'm going to go ahead and take these in the order they came in. We'll address as many of them as quickly as we can. So the first one goes back to radar and LiDAR. And so it starts out, how would the model distinguish if the patent says, for example, LiDAR or radar? Now, but prefaced, granted, if that is optional, then there may be another subclass where the patent should be classified into, for example, self-driving auto that uses LiDAR or radar. So that's probably the best part of that question is, how is it then that it distinguishes the method from the objective? And so the objective ultimately here is self-driving or autonomous driving, more so than the specific implementation, the LiDAR or the radar. So in the development of those 114, how would that get shuffled?
Yeah, so that's actually more of a question or more of an issue in taxonomy design than in the software. The software is very capable of making that distinction if you wanted to, but we tried to, it's a technology taxonomy, not an application taxonomy. So we tried to, as far as possible, keep the classes in the taxonomy to be technology. So LiDAR and not self-driving cars. The example you gave of it could be implemented with LiDAR or radar is extremely common, and the algorithm just makes a judgment call on which one it should fall into. And that is, it's definitely a weakness of this approach, but it's kind of necessary, as you talked about earlier, for all these, where you want a really quick, easy to understand summary. At the end of the day, you've got to kind of assign it somewhere to make it possible to analyze the results easily.
Yeah, well, we've talked about that. There's a trade-off. If you want multiple buckets, there's a different way to do that.
Right.
And otherwise, there is some real value in saying, look, it's primarily this. All right. And yes, that might be mentioned, but it's primarily this. So, okay, great. All right, next one. We haven't really talked about the relationship with the patent classification coding systems. So we had a question, are classification codes being used? And so generally speaking, where is it that this relates, I suppose, to the use of the IPC or CPC?
Yeah, the inputs to the model are the text of the patent, title, bits of the background, claims, abstracts, and also the class codes. But when we experimented with, we deliberately withheld the class codes from it, and we deliberately withheld the text from it as a way to try and figure out which it was relying on more. if you withhold the class codes, it makes very little difference to the accuracy. It drops it by a few percent. If you withhold the text, it's useless. So we're pretty confident that it's almost exclusively using the text. It occasionally uses class codes to disambiguate or to help it, probably to help it figure out if this is more LiDAR or more radar related. But in common with other things, other observations we've made and the papers that we wrote for the Elsevier journal, the class codes really don't correlate that well to the actual technology of the patent.
Okay, great, thank you. And like I said, I'm looking through the questions, and I think you just addressed this one. Although maybe you want to put a finer point on it. The question is, what is being used as the inputs? Abstract, patent metadata, inventor, assignee, class codes, claims, combination of these, or the entire specification. And it says including diagrams. So my guess is that there's no way to incorporate diagrams. But what portions of the documents are typically being used as the mechanism by which the model works upon?
Yeah, so for this classifier, it's not the same as our binary. It's actually a completely different technology to our binary classifiers. We're using class codes, title, abstracts, claims, and some of the background. The first two sections, I think, which are novelty and something else, I forget exactly what they are. But it doesn't use citations, it doesn't use inventors, it doesn't use assignees, it doesn't use any of that information. It tries to stay as neutral as possible. And to predict another question, where we're dealing with like Chinese language or Japanese language, we use machine translations into English, and then we classify based on the English machine translation.
Okay, fantastic. We had a request for a link to that particular paper. So if there's a link to the UTT paper available, that would be good to have.
I think it might be in the handouts, but if not, you can find it on the Cipher website, I believe.
Okay.
Cipher.ai.
Yeah. Okay.
And you can, there's also
this is
the complete taxonomy with all the scope notes as well, so you can see where we've drawn the distinctions between the technologies and how we've. There's lots of things where, like example we were playing with earlier today is PIR sensors, motion sensors, and infrared sensors. Like where do PIR sensors belong? Are they closer to infrared sensors or are they closer to motion sensors? That's a good example where you just got to make a call as a human where you want things.
Yeah, I don't know whether that question about the paper was when you just cryptically referred to the Elsevier paper. That was a World Patent Information paper that Tony co-authored with us called Gold Standards Classification. And we definitely, I think Tony, you've probably got the link to that. I can't access it while I'm on the webinar, but it was World Patent Information Gold Standards by Harrison Trippi.
Yeah.
Yeah, and of course on the ML4Patents.com site, that's one of the pinned. So if you go to the evaluation sets section, that one's pinned, because it's one of the key papers that have come out in the past couple of years that talk about means by which you can use these gold standard collections for doing these sort of evaluations. Okay, so this is a great question. Are there any plans of making the UTT more granular in the future? So now that you've got this core collection, and you talked a little bit about on a yearly basis re-examining, but maybe are there plans at some point to say, well, okay, 114 started off, that's great, that's fit for purpose, really useful, and now we're ready to take on that next frontier and make it even a little more granular still.
Yeah, so I think one of the things we're definitely going to do with this year's update is break down some of the larger classes into 2 or 3. We don't have any concrete plans. I mean, the other thing that we could do is go down one more level. So you've got 9 superclasses, 114 subclasses. We could have another, I don't know, 300-400 subclasses, but that's probably not something we're going to be taking on in the near future. And frankly, once you're down at that level, you're probably better off with a bespoke taxonomy, because if you get too granular, it becomes very subjective and very terminology grounded. Like what one company calls a semiconductor substrate, another company will call something completely different, and it becomes much more arguable where things belong.
And it's really important, but it's a really important point, Tony, about whether it's enough, whether 114 is too high level. Remember, we set out on our mission to create a taxonomy that fairly cut the world's patent portfolio, the world's patents into 114 buckets. We knew, bearing in mind the number was 44 million, we knew exactly how big each bucket would be, and the answer is very. But we took as our guiding light what happens in economics, what happens in the corporate world. And there are lots of classification systems, whether it be the SIC code system, which is the UK way of classifying companies, or NAICS and GICS in the US for classifying the activity. They all work at this kind of 100 to 150 level, and they get on just fine because it gives the disadvantage of high level, but the advantage of accessibility, uniform speed, repeatability, consistency. And so that's the trade-off. I think I would definitely worry about rushing into another level of granularity.
Okay, great. We've got one last question here. I think it's been addressed to a certain degree. We've also 3 minutes to the top of the hour. We're perfect on time. Many people have stayed with us, which again, thank you very much. Please fill out the survey. Please grab the handouts. But this one asks a little bit more about UTT versus patent classification code systems. And so the question, I'll just read it. Have you checked the UTT against a patent classification scheme to see how diverse the patent classifications are within each UTT subclass, where the patent classification may be at some high level of granularity as well? And so I think that's an interesting question, at least maybe from an academic perspective, because of course, when you get to class, subclass, I forget what it is, it's up to like 120,000 when you get all the way
600,000.
Yeah, see, so it's an even larger number. It's a level of granularity that is fantastic for what the examiners need to do to decide who's going to look at this thing. But you almost always end up saying, well, okay, let's just take the first 8 digits. Let's just take the first 4 digits. Let's just take the first 3 digits. You end up segmenting it anyways in order to be doing something useful where you don't have everything at 1.5% and then one thing at 3%, which is not useful. Everybody just, your head swims. So, but have you looked at all within the 114 about which ones tend to cover more classes or cross classes or anything like that? I mean, I recognize that there may not be a business case for that.
No, it would be very interesting academically. We haven't done that work. We know from previous work that class codes don't correlate to technology. The class codes exist they're there to help the examiners find citations, right? So they're focused on particular features of the invention. They don't really correlate to technologies that much. In some rare cases they do. There's a few class codes which are highly tied to a particular technology, but a lot of the time the sort of underlying technology of the invention isn't really captured by the class codes. I can say that with a degree of confidence because we know that if you only give the classifier class codes, the results are very poor. So we can be pretty confident that there's not a high relationship between the two factors, but it would be an interesting study to find out exactly how disparate the class codes are across the UTT classes.
And I know we're running out of time, but for those people who want to access your gold standard collection on qubits, we know because a man called Tony Trippi told us they were all positive to the qubit definition, which you published also. And then you can have a little look at the class codes associated with those, and you will see an amazing array of class codes. And if you'd have run it the other way around, taken those class codes, you would have ended up with things that were very definitely negative to the class you constructed.
Oh yeah.
That's partly because quantum computing is quite new, but it's also true even in ancient technologies. You can take something like vehicle brakes. There's still a very, very poor correlation between class codes and technologies.
Well, we're at 1 minute after. And again, thank you everybody who participated today. There will be, I had a question, I answered it and sent it out publicly. But of course, tomorrow everybody will get an email. And that email will contain a link to this recording. All right. And of course, please fill out the survey. Let these guys know if they can assist, if they can get in touch with you to provide even more details or provide access. But again, thanks everybody. Been a little while since we've done one of these for a variety of different reasons. Great to be back. Great to be talking with good friends and people who are such huge supporters of this industry. So again, Nigel, Steve, thank you so much. Excellent job and congratulations on the UTT.
Thank you, Tony.
Thanks, Tony.